Hello, my dear students. Welcome back to my class. Most probably, this class is my second last class because according to the government, I got 5 classes and today I'm doing 4-day recording. Okay, so without wasting our time, let's start the class. Okay, so today, as we have discussed the real depth, apparent depth, right? Why the bottom of the water tank, when we fill with water, it appears to be raised, right? So I gave you one formula, mu equal to real depth divided by apparent depth. So by using this formula, sometimes numerical question might ask in the exam. So I'm going to discuss one numerical that already in our textbook. Okay, so I have already written the question over here. So first, see the question. Please focus on the question. Okay, so okay, now you see a tank is filled with water to a height of 12.5 centimeter. Okay, a tank is filled with water to a height of 12.5 centimeter. The apparent depth of a needle, right? We have placed a needle on the bottom of the tank. So needle lying at the bottom of the tank is measured by a microscope to be 9.4 centimeter. So what is the real depth? Real depth is 12.5 centimeter, and what is the apparent depth? Apparent depth is 9.4 centimeter. So they are asking what is the refractive index of water. Okay, so this is the first part of the question, and next part again we have if the water is replaced. Initially the tank was filled with water. Now we are going to replace the liquid. If the water is replaced by a liquid of refractive index of 1.63. Okay, now we have replaced the water by it may be any liquid, but they have given the refractive index of that particular liquid is 1.63 up to the same height. Okay, real depth will be same, okay, because they have mentioned up to the same height, means the real depth is same again like before. By what distance would the microscope have to be moved to the focus to focus on the needle again? Means in the next part of the question we have to find the apparent depth. Okay, so let's solve the first part of the question. Okay, so solution here. Okay, so we'll write what we have given. So we have given real depth. Real depth. So generally real depth is denoted by H1. Okay, so real depth H1 it's given in the question. This is 12.5 centimeter. This is 12.5 centimeter. Again, apparent depth is also given. So apparent depth. Say this is H2. So this is 9.4 centimeter. Then what we have to calculate? What is the refractive index of the water? So we have a formula. So we'll write we know that refractive index is given by real depth divided by apparent depth. So what is the value of real depth? It's 12.5 centimeter. And what is the value of apparent depth? This is 9.4. So if we use calculator, the answer will be 1.33 approximately. So I'm writing here approx. Okay. So this is the required refractive index of the water. So we have solved the first part of the question. Now we'll solve the second part of the question. Okay. Okay, now this is part 2. Okay, in the part 2, I have already told you we have to find the apparent depth. Okay, now here, if water is replaced by a liquid having refractive index. Say this is new refractive index, so I'll take the symbol as mu dash, or you can take in place of the refractive index you can use small n also. Okay, now here I am using mu, so this is mu dash. Say if the water is replaced by a liquid having refractive index mu dash. Say this it's already given. This is 1.63. Okay, so we have to find the new apparent depth. So therefore new apparent depth. B, say this is y, okay? So we have considered new apparent depth to be y. Okay, so real depth will be same. Why? Because here they have already mentioned one up to the same height. So real depth will be same. So for the same, for this numerical also, we'll take h1 is how much? 12.5 centimeter. Okay, so we'll use the same formula. We know that. Okay. We know that, say here, this mu dash equal h1 divided by y, okay? So what we have given? We have given mu dash and h1, we have to calculate y. So I'll transfer to the other side. So h1 divided by mu dash. So this is, what is the value of h1? This is 12.5. And what value of mu dash? This is 1.63. So after calculation, if we calculate this one, so the answer will be 6.76, okay? So this is centimeter, okay? Is it clear? Okay, 6.76 centimeter, okay. Now, we got the apparent depth, we got the refractive index, but there is again third part of the question. So they are asking, by what distance would the microscope have to be moved to focus on the needle again? Okay, now you compare the new apparent depth with the earlier apparent depth. Which one is greater? This one is greater. So to adjust, to focus on the needle, we have to move up the microscope, okay? So here I am writing for the last part, okay? So therefore, microscope have to move up to a distance by just, this is 9.4 minus 7.67. This is 1.7 centimeter. So this is the answer, okay? So we got the refractive index. This is part 1, answer for the part 1, and this is answer for the part 2, okay? So this is one important question. So next, we'll switch to the different topic. This is total internal reflection. Total internal reflection. Okay. So first, I'll give you the definition later on. First, I'll explain what is total internal reflection with the help of a diagram. So this is rarer medium, and say this is denser medium, denser medium. So rarer medium, we can take this is air medium and this is water medium. So this is medium 2. This is medium 2, and this is medium 1. Okay. Now it's a little bit different case. Here, the ray of the light is traveling from denser medium to the rarer medium. Okay. Okay. So this is a source of light, and from here the light is traveling from this particular point, from this medium to that medium. So before discussing this total internal reflection, we must know what is internal reflection. So first, you have to know what is internal reflection. Internal reflection. What is internal reflection? Okay. Internal reflection. Okay. So what is internal reflection? So when a ray of light traveling from denser medium to the rarer medium encounters a transparent medium, what happens? Some of the light, means some part of the light reflected back to the same medium. Okay, you got it right? When the ray of light traveling from one medium into another medium. Okay, at the interface, some of the ray reflected back into the same medium, say like this, reflected back into the same medium, and some part of the ray travel to the other medium. So this is travel to the other medium. Okay? So here two phenomenon is taking place. The ray of the light is traveling from denser medium to rarer medium. So some part of the ray is reflected back to the same medium, and some part of the ray is traveling to the another medium. This kind of situation or this phenomenon is called internal reflection. Okay? So what happens in the internal reflection? Out of 100% light, some portion will reflected back into the same medium, and the rest of the light travel into the another medium. And this situation is called internal reflection. Okay? So here we can take, this is O1, say point of incidence, and here I am drawing normal to the interface. Okay. So this is again normal to the interface. So this is N. So this is O2. So I'll take this N1, normal 2, and normal 1 and normal 2. Okay. Here also same case is happening. Some part of the ray is reflected back to the same medium, and some part of the ray is traveling to the another medium. Okay. Now, this is N3. Okay. But see, here the different phenomena is taking place. Here the refracted ray grazes along the interface. This is interface between two medium. Here, the refracted ray grazes along the interface. So in this particular case, we'll get the new term which is called critical angle, which is called critical, here I am writing here, critical angle. So generally critical angle is denoted by C in some reference book, or in our textbook it is denoted by IC. Okay. So what is critical angle? Now it's very easy. When the ray of light is traveling from one medium, means from denser medium into rarer medium. Okay. So when the light ray incident in such an angle for which angle of reflection is 90 degree. Okay. So for answer for this critical angle, we can write critical angle for pair of medium can be defined as the angle of incidence in denser medium for which the angle of refraction in rarer medium is 90 degree. Is it clear? So I repeat, critical angle for a pair of media can be defined as the angle of incidence in denser medium for which the angle of refraction in rarer medium is 90 degree. Okay. So this is clear. So you have to remember one thing. When we got the critical angle, this refracted ray always grazes along the interface. Here we are taking another ray. Okay, so this is IC greater than I greater than IC. Okay, and here, okay, now in the first two cases, some of the light is reflected back and some are traveling to the other medium. But here the refracted ray grazes along the interface. And this in fourth stage, okay, what's happening here? There is no refraction, there is only reflection. So this case is called total internal reflection. This case is called what? Total internal reflection. So what is total internal reflection? When the ray of light incident at an angle greater than critical angle. Okay. When the ray of light incident at an angle greater than what? Critical angle. All the rays will suffer reflection. That kind of reflection is known as total internal reflection. Okay. So definition is important. I'll give the definition. I'll write on the board. So total internal reflection definition is very important, so I'll write on the board. Okay. So in short, in some book, it's written as TIR. It means total internal reflection. May be defined as the reflection phenomenon. Reflection phenomenon that takes place when ray of light traveling from denser medium to rarer medium get incident at an angle greater than critical. Get incident, you can write at the interface, get incident at the interface. Get incident at the interface at an angle greater than critical angle. Okay, so this is the definition for TIR, or total internal reflection. So what is total internal reflection? It is a reflection phenomenon for the light traveling from denser medium to the rarer medium when the ray of light incident at an angle greater than critical angle. Okay, but sometimes in exam conditions for total internal reflection also ask. Okay, so under what condition the total internal reflection takes place? There are two conditions. First condition, the ray of light must travel from denser medium to the rarer medium. Is it clear? So first condition to happen total internal reflection is the ray of light must travel from denser medium to the rarer medium. Next, the angle of incidence of the light must be greater than critical angle of the, you can write critical angle of pair of media. Is it clear? I hope it's clear. Now we have discussed, we have already discussed what is internal reflection, what is critical angle, and what is total internal reflection. Okay, now we'll try to find the relation between refractive index and critical angle. Next is relation between critical angle and refractive index. So this is our next topic, relation between refractive index and critical angle. Okay, so you can write, so according to Snell's law, refractive index of rarer medium. Rarer medium is medium 2 in case of total internal reflection. Rarer medium with respect, when I write WRT, it means that with respect to denser medium. This is medium 1 is given by. Okay, why I am writing from denser to rarer? Because this is the case of total internal reflection. If there is no total internal reflection, we won't get the new parameter, that critical angle. So I am writing the refractive index of rarer medium with respect to denser medium, because ray of light is traveling from denser medium to rarer medium. So it's given by, so n. So this n represents the refractive index, or if you want, then you can use mu also. Now I am using n. So this is n, refractive index of medium 2 with respect to medium 1. This is n to 1. We can write sin I, angle of incidence divided by angle of refraction. So this is equation number 1. Okay. So when the light is incident at an angle equal to critical angle, here IC. Okay. What if when the light is incident at an angle greater than critical angle? So here the case is like this. So ray of light, so this is normal, and this angle is IC. Then what happens? the refracted ray grazes along the interface. So in this particular case, our angle of refraction must be 90 degree. So when angle of incidence means I equal to IC, this implies that angle of refraction is 90 degree. Whenever the light ray incident at an angle equal to the critical angle, so our angle of refraction must be how much? 90 degree. So now we will put this condition in equation number 1. So now 1 implies, so n to 1 equal sine, in place of I we have critical angle, so I am writing I suffix c, and in place of r we got 90 degree. So what is the value of sine 90 degree? That is 1, right? So value of sine 90 degree is 1. So n to 1 sine IC, the value of sine 90 degree is 1. So we can write n to 1 equal to sine IC. So this expression also represents the relation between refractive index and critical angle. Or we can further modify this equation. Say, I'll show you the modification. We can modify like this also, IC equal to sine inverse of n to 1. Or we can modify 1 by n 1 2, because we have already learned in the principle of reversibility, the refractive index of medium 2 with respect to medium 1 is reciprocal of refractive index of medium 1 with respect to medium 2. So I am writing n to 1, in place of n to 1 I am writing 1 by n 1 2. So this is sine IC. So this is also another relation, and again one more important relation is n 1 2 equal to 1 by sine IC. This is a simple mathematical expression. Okay. So these four expressions are the these four expression represents the relation between critical angle and refractive index of pair of media. I hope you got this one. Sometimes small question might ask, they might give you the refractive index and they will ask you what is critical angle. Sometimes they might give you what is sometimes they might give you the critical angle and you have to find the refractive index. Okay, so next we will discuss the total internal reflection in nature and how we can use in technology. So next topic is TIR, means total internal reflection in nature and its technological use, or you can write technological applications. Okay. So in the class 12 book also there are very common phenomena are there that we have already discussed in class 10. So here I'll just tell you, but I'm not going to explain all this common phenomena because you already know. First one is mirage. So this is what we already got in class 10. Next is brilliance of diamond. Next is brilliance of diamond. Means why the diamond sparkle. And third is total internal reflection in prism. This one I'll discuss now. And fourth one is optical fiber. Optical fiber. Okay. Optical fibers. Okay. So I think you guys already know what is optical fiber, because these days to transmit data from one place to another, because we in India also we are using the high speed internet data like 4G, 5G, right? For all this kind of data transmission, we use optical fibers. And that the traditional one that we have used in years before was known as coaxial cables. So when you set up LAN, suppose you set up LAN, local area network in your building, what kind of what kind of fiber you use for transmitting data? These are the coaxial cables. But for the high-speed internet data and for high-speed data transmission, these days the technology used is optical fibers. So this is very important. So it's just a theoretical part, so you can go through the book. So now I'll discuss the prism, total internal reflection in prism. Okay, so you have to remember this prism. What is the use of prism? So first you have to know, okay, prism may be made up of flint glass and crown glass. Okay, so flint glass means like flint glass, or here in book it is written dense flint glass, and this is crown glass. Ground glass. These are the glass materials by which we made prisms. So we have to know the critical angle. We have to know the critical angle of the prism. It's ranging from 41.14, or sometimes we use 37.31. Because when we discuss total internal reflection, critical angle is very important, because light must have to incident at an angle greater than the critical angle. Okay. Now, so prism. What is the use of prism? So there are two uses of prism. Prism is used to bend the light by 90 degree or 180 degree, make use of total internal reflection. So what is the use of prism? We use the prism to bend the light ray by 90 degree, or sometimes by 180 degree, by using the phenomenon what we call critical angle. And the next use is we used prism in binoculars or in some other optical instruments to invert the images without changing their sizes. Okay, now I'll show how we can bend the light by 90 degree by using prism. So this is a prism. Okay, so this is a prism. So this angle is 90 degree, as you can see, and this is 45. Here I'm writing outside, okay, because of space. So 45 degree, and 90 degree. Suppose a ray of light hit this or is incident on the face of the prism. Means the ray of light is incident on the face of the prism normal, means at perpendicular direction. Okay. The ray of light is incident on the face of the prism normally. So what happens? It will passes through the same path and hit the second face of the prism. Okay, here. So let me draw a normal to this interface. So this angle is 45 degree. Why? If this angle is 45 degree, this angle must be 45 degree. Now, what is your angle of incidence now? This is 45 degree, right? So now you check the critical angle of the prism. So this 45 degree is greater than 41 degree or 37 degree. So if the angle of incidence is greater than the critical angle, there must be total internal reflection. Okay. So light was supposed to come out on this face, but light will suffer total internal reflection. So its path will be like this. Okay. So now this ray of light is incident on this face of the prism normally, so it will directly come out from the prism. So it was supposed to get refracted, but because of its angle of incidence is greater than critical angle, it is suffering total internal reflection. So now how we calculate the bending of light? Now you see, this is the actual path of the light, right? So light was supposed to travel in this direction. Light was supposed to travel in this direction, but by using prism, we bend the light by this direction, right? By this direction. So this is this much angle, light is bent along its path. So this angle is how much? 90 degree. So this is how we can bend the light by 90 degree by using prism with the help of total internal reflection. Okay, next I'll show you how we can bend the light by 180 degree. So this is prism again. Okay, so this is 90 degree. This is 90 degree, and this is 45 degree, and this is 45 degree. Okay, so here, so light, okay, I have already explained, okay, so it is hitting the surface normally, so it will follow this path, and here, the angle is 45 degree, and this 45 degree means greater than critical angle, it will suffer total internal reflection, and it will hit the second face. Now you draw the normal here, okay. So again, this angle is 45 degree again. Again, the angle of incidence is 45 degree, okay. So again, it will suffer total internal reflection, and it will come out like this, okay. Is it clear? Okay. So now here, light was supposed to travel in this direction, but we have bent the light, direction of light. How much? By 90 degree. Again, here light was supposed to travel in this direction, but from this we bend the light by 90 degree. So 90 plus 90, how much? 180 degree. So this is how we bend the light by 180 degree by using prism. Okay, so one more important thing, the prism, this technology is used in binoculars. Used in where? Binocular, to form the erect image and to remove the lateral inversion. So do you know what is lateral inversion? When you stand in front of the glass, or in front of the plane mirror, when you show your suppose right hand, in mirror you'll see your left hand, right? When you see your left hand, you'll see the right hand. This is called lateral inversion. Okay, so by this lateral inversion can be removed by using the prism, by using this total internal reflection. Okay, so I'll show you how we can invert the image by using prism. So this is a prism. So this is 45 degree and this is also 45 degree. Okay, since we're discussing about the image, so we need two rays. So this is two rays. These are the parallel beam of light, and here is the image. So this is image. So this is A, so A, B. Okay, here they will suffer total internal reflection, total internal reflection, and they will come out like this. And here also they will suffer total internal reflection and they will come out like this. So this is the direction of the light. And here, so now you see the first ray and the second ray, and here is the image. And this is a B dash, A dash. So this is the diagram or the ray diagram showing how we can invert the image by without changing the size of the image. So dear students, so today I am stopping the class just before 2 or 3 minutes, only because in the next classes we are going to discuss refraction through the spherical surface. It will take 7 minutes or 8 minutes. So I'll discuss everything in the next class. Until then, bye. Eat healthy, stay healthy, and don't forget to study. You just practice everything, whatever I have given here, you write and you practice it, and you try to utilize your time in proper way. Bye everyone.